Reactance is a term used in connection with impedance in alternating current circuits. It represents the opposition to the flow of alternating current caused by the presence of either inductance or capacitance in the circuit. Reactance opposes the flow of alternating current just like resistance opposes the flow of direct current. Reactance is a reactive property that causes a phase shift between voltage and current in the circuit. There are two types of reactance. Firstly, inductive reactance, which is caused by the presence of an inductor in the circuit. It opposes the flow of alternating current by generating a magnetic field that opposes the change in current. Secondly, capacitive reactance, which is caused by the presence of a capacitor in the circuit. It opposes the flow of alternating current by storing electrical energy and releasing it out of phase with the applied voltage. Impedance is the total opposition to the flow of alternating current in a circuit. It includes both resistance and reactance. In an alternating current circuit with only inductance or capacitance, impedance is equal to the reactance, that is, impedance is equal to inductive reactance or capacitive reactance. The presence of both inductance and capacitance in a circuit results in a complex impedance that includes both resistance and reactance. Reactance is important in alternating current circuits because it affects the current flow and phase relationships. It is used in applications such as tuning resonant circuits such as in radios, filtering unwanted frequencies, and designing electronic circuits with specific frequency responses. Inductive reactance, denoted as X sub L, is the opposition to alternating current flow offered by an inductor. Inductors store energy in a magnetic field, and this energy storage process impedes the instantaneous changes in current. The inductive reactance is directly proportional to the frequency of the alternating current and the inductance of the inductor. The formula for inductive reactance is X sub L equals 2 times pi times F times L, where X sub L is the inductive reactance in ohms, F is the frequency in hertz, and L is the inductance in henries. A higher frequency or a larger inductance will result in a greater inductive reactance, thus impeding the alternating current flow more significantly. Inductors are commonly used in circuits to filter alternating current signals, suppress noise, and store energy. For example, in power supplies, inductors are used to smooth out voltage fluctuations and provide a stable direct current output. In radio frequency circuits, inductors are used to tune to specific frequencies and filter out unwanted signals. Capacitive reactance, denoted as X sub C, is the opposition to alternating current flow offered by a capacitor. Capacitors store energy in an electric field, and this energy storage process impedes the instantaneous changes in voltage. The capacitive reactance is inversely proportional to the frequency of the alternating current and the capacitance of the capacitor. The formula for capacitive reactance is X sub C equals 1 divided by 2 times pi times F times C, where X sub C is the capacitive reactance in ohms, F is the frequency in hertz, and C is the capacitance in farads. A higher frequency or a larger capacitance will result in a smaller capacitive reactance, thus allowing more alternating current to flow. Capacitors are commonly used in circuits to filter alternating current signals, store energy, and provide timing functions. For example, in audio circuits, capacitors are used to block direct current and allow alternating current signals to pass, thus separating the audio signal from any direct current bias. In power supplies, capacitors are used to smooth out voltage fluctuations and provide a stable direct current output. In timing circuits, capacitors are used to create delays and control the timing of events. Impedance, represented by the symbol Z, is the total opposition that a circuit presents to alternating current. It is a more general concept than resistance because it takes into account both resistance and reactance. Resistance, denoted as R, is the opposition to current flow that dissipates energy in the form of heat. Reactance, denoted as X, is the opposition to current flow that stores energy in either a magnetic field inductor or an electric field capacitor. Impedance is a complex quantity that has both a magnitude and a phase angle. The magnitude of impedance, denoted as Z, is the total opposition to current flow and is measured in ohms. The phase angle, denoted as theta, is the phase difference between the voltage and current in the circuit and is measured in degrees or radians. The formula for impedance is Z equals the square root of R squared plus X squared, where Z is the magnitude of impedance, R is the resistance, and X is the reactance. Phase angle is given by theta equals arctangent of X divided by R. In a purely resistive circuit, the impedance is equal to the resistance, and the phase angle is 0 degrees. In a purely reactive circuit, the impedance is equal to the reactance, and the phase angle is either plus 90 degrees for inductive reactance or minus 90 degrees for capacitive reactance. In a circuit with both resistance and reactance, the impedance is a complex quantity that depends on the values of both the resistance and reactance. Impedance is important because it determines the amount of current that will flow in a circuit for a given voltage. It also determines the phase relationship between the voltage and current. Understanding impedance is essential for designing and analyzing alternating current circuits. Resonance occurs in an alternating current circuit when the inductive reactance and capacitive reactance are equal in magnitude. At resonance, the impedance of the circuit is at its minimum and the current flow is at its maximum. Resonance circuits are used in a variety of applications, such as tuning radios, filtering signals, and creating oscillators. The resonant frequency, denoted as f sub 0, is the frequency at which resonance occurs. It is given by the formula f sub 0 equals 1 divided by 2 times pi times the square root of L times C, where f sub 0 is the resonant frequency, L is the inductance, and C is the capacitance. At resonance, the inductive reactance is equal to the capacitive reactance, so X sub L equals X sub C. This means that 2 times pi times f sub 0 times L equals 1 divided by 2 times pi times f sub 0 times C. Solving for f sub 0 gives the resonant frequency formula. Resonant circuits are used to selectively amplify or attenuate signals at specific frequencies. For example, in a radio receiver, a resonant circuit is used to tune to the desired radio station. The resonant circuit amplifies the signal at the frequency of the radio station and attenuates signals at other frequencies. Filters are circuits that are designed to pass signals at certain frequencies and block signals at other frequencies. Filters are used in a variety of applications, such as audio processing, image processing, and communications. There are several types of filters, including low-pass filters, high-pass filters, band-pass filters, and band-stop filters. A low-pass filter passes signals at frequencies below a certain cutoff frequency and blocks signals at frequencies above the cutoff frequency. A high-pass filter passes signals at frequencies above a certain cutoff frequency and blocks signals at frequencies below the cutoff frequency. A bandpass filter passes signals at frequencies within a certain range and blocks signals at frequencies outside the range. A bandstop filter blocks signals at frequencies within a certain range and passes signals at frequencies outside the range. Filters are typically constructed using resistors, capacitors, and inductors. The values of the components are chosen to achieve the desired frequency response. For example, a low-pass filter can be constructed using a resistor and a capacitor. The cutoff frequency of the filter is determined by the values of the resistor and capacitor. Power factor is a measure of how effectively electrical power is being used in an alternating current circuit. It is defined as the ratio of real power to apparent power. Real power is the power that is actually used to do work, while apparent power is the product of the voltage and current in the circuit. Power factor is a dimensionless quantity that ranges from 0 to 1. A power factor of 1 indicates that all of the power in the circuit is being used to do work, while a power factor of 0 indicates that none of the power is being used to do work. A low power factor can result in increased energy costs and reduced system efficiency. Power factor correction is the process of improving the power factor of an alternating current circuit. This is typically done by adding capacitors to the circuit to compensate for the inductive reactance. The capacitors supply reactive power to the circuit, which reduces the amount of reactive power that must be supplied by the source. This improves the power factor and reduces the amount of current that flows in the circuit. Power factor correction is important for large industrial and commercial facilities that use a lot of electrical power. By improving the power factor, These facilities can reduce their energy costs and improve the efficiency of their electrical systems. Skin effect is a phenomenon that occurs in alternating current circuits where the current tends to flow near the surface of the conductor rather than uniformly throughout the cross-section. This is because the alternating current creates a magnetic field that induces eddy currents in the conductor. The eddy currents oppose the flow of current in the center of the conductor, causing the current to concentrate near the surface. The skin effect becomes more pronounced as the frequency of the alternating current increases. At high frequencies, the current may only flow in a thin layer near the surface of the conductor. The skin depth is a measure of the depth to which the current penetrates into the conductor. It is defined as the distance from the surface of the conductor at which the current density has decreased to 1/E, which is approximately 37% of its value at the surface. The skin depth is inversely proportional to the square root of the frequency. The skin effect can have a significant impact on the performance of alternating current circuits. It can increase the resistance of the conductor, which can lead to increased power losses. It can also change the inductance of the conductor, which can affect the impedance of the circuit. To minimize the skin effect, conductors can be made from materials with high conductivity or can be designed with a large surface area. For example, conductors can be made from copper or aluminum, or they can be stranded or hollow. Transmission lines are used to transmit electrical power over long distances. They typically consist of 2 or more conductors that are supported by insulators. The characteristics of a transmission line, such as its impedance, capacitance, and inductance, can affect the performance of the power system. The impedance of a transmission line is the opposition to the flow of alternating current. It is determined by the resistance, inductance, and capacitance of the line. The capacitance of a transmission line is the ability of the line to store electrical energy. It is determined by the geometry of the conductors and the insulating material between them. The inductance of a transmission line is the ability of the line to store magnetic energy. It is determined by the geometry of the conductors and the spacing between them. The characteristics of a transmission line can be affected by factors such as the frequency of the alternating current, the length of the line, and the temperature of the conductors. Transmission lines are designed to minimize power losses and maintain a stable voltage. Transformers are used to increase or decrease the voltage of alternating current. They consist of 2 or more coils of wire that are wound around a common core. The voltage ratio of a transformer is equal to the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. Transformers are used in a variety of applications, such as power distribution, electronic circuits, and audio equipment. They are an essential component of modern electrical systems. The core of a transformer is typically made from a ferromagnetic material such as iron or steel. The ferromagnetic material concentrates the magnetic field, which increases the efficiency of the transformer. The core is often laminated to reduce eddy current losses. Eddy currents are circulating currents that are induced in the core by the alternating magnetic field. These currents dissipate energy in the form of heat, which reduces the efficiency of the transformer. Lamination reduces eddy current losses by breaking up the core into thin layers that are insulated from each other. This prevents the eddy currents from flowing freely, which reduces their magnitude. In summary, reactance is a crucial concept in alternating current circuits that describes the opposition to current flow due to inductance and capacitance. It is important to understand reactance in order to analyze and design alternating current circuits effectively. It affects current flow, phase relationships, resonance circuits, filters, power factor, skin effect, transmission lines, and transformers.